Okay, so chapter 7 describes some proof techniques for proving non-conditional statements. In all the statements, all the techniques we have so far, direct proofs, and in particular direct proofs and contrapositive proofs, you can use to prove if-then statements. You can also use contradiction to prove if-then statements. But now we're going to look at things that are not if-then conditional statements. Okay, so chapter 7 is about proving non-conditional statements. The first section that I want to talk about is 7.1 talks about if and only if proofs. Okay. So we showed that the statement, the biconditional statement P if and only if Q, we showed that this is equivalent to two conditional statements. P implies Q and Q implies P. So that's kind of the symbol for if and only if is instructive here. I mean, it has two implications. P implies Q and Q implies P. So we showed that this is actually logically equivalent to P implies Q and Q implies P. Okay? So you have the forward implication, P implies Q, and then the converse, Q implies P. So the way the proofs for an if and only if statement often goes is you actually write two little proofs. You write this proof, assume P, show therefore Q, and then you do another proof, assume Q, and then prove P.
So it's kind of like
yeah, it's kind of like cases, but it's two. You have two different steps, and it's important. Now, when you're doing cases, you kind of delineate your cases, like case 1, case 2. So when you're writing your proofs, you would say you somehow let the reader know you're doing this part, and then you do this part. And I'll show you two ways that people often use to show these.
We will assume P implies Q.
Right. So you might say, yeah, just the words. First, we'll show that P implies Q, and then you do it. And then you start a new paragraph. Now we'll show that Q implies P. So I'll show you some examples. So it's really like two short proofs in one. Okay. Yes.
Before you break it down like cases, you're gonna put that fact in it, and then in the bottom say because of.
No, I mean we'll just know, like if you have an if and only if statement, this is often read P if and only if Q. Okay, to prove that statement, some proofs you can prove one implies the other and vice versa, but usually you break it down into two parts, two halves of your proof. First you show that P implies Q, then you show Q implies P. Therefore, we have the statement P. Yeah. But let me give you an example, okay? So now, when you're doing, this little piece, you could use a direct proof. You could use a proof by contrapositive. You could use a proof by contradiction. So it's kind of like it is kind of like two different proofs, and they're all. But the way you write it, it makes sense that they're together. Okay. All right. So let's see. Okay, I guess I have room here. All right. So here's an example. A, B, C, natural numbers. Prove A divides B if and only if AC divides BC. All right, so this is my P if and only if Q. So first, usually I just do the forward kind of implication. I'm first going to assume that A divides B, and I'm going to conclude that AC divides BC. Okay. First, we show that A divided B implies AC divides BC. Okay, so you kind of give the reader a clue as to what the order of your proofs. I mean, you don't have to do that first. You could have done Q implies B first, but you know, it's nice to let the reader know what you're doing. All right, this is just a direct proof. What does A divides B mean? Yeah. Well, now here's the thing. There's a C in the statement of the theorem, so you can't really use C for your arbitrary factor. Yeah, so I would use D. So that happened a couple times, I think, in the last homework assignment. If there's a C already used in the statement of the proof, you can't. That's not arbitrary anymore. It's kind of taken. So use a different letter. Okay. It didn't affect the proof too much, but you really have to use a different letter if you're going to scan for, because you don't really mean the same exact C that they mean. Okay. So first we show that A divides B implies AC divides BC. Okay. So then B equals A times D for some integer D. Okay? So then how would we finish the proof? I think you guys had this as a homework problem, right? So we need AC divides BC. I think this is a homework I just handed back, right? So how could you, if AC divides BC, BC looks like AC times an integer. So I have this equation, what do I need to do?
So AD times C equals A.
Yeah, I need a factor of C on both sides, right? So I'm just going to multiply both sides by C. Okay. Multiplying.
Why is D an integer if A, B, and C are natural numbers?
Well, I mean, you do know this is the minimum amount you need to assume. For the definition of divides, I mean, are you claiming it's not an integer?
Well, I'm just saying, because A, B, and C are natural numbers.
So have you proved that if A and B are natural numbers, then D is a natural number? We haven't really proved that. I mean, it's true, but this is the minimum I need to assume. I mean, for division, we need to. It's an integer multiple of B is an integer multiple of A. So it's not wrong to put that. It's just technically not part of not the definition. So you really are assuming more if you assume it's a natural number. Okay, that's a good point. I mean, it is true. I mean, you know, right? If B is positive and A is positive, then D better be positive. Okay, so multiplying both sides by C gives BC equals, now, is it too sneaky to multiply right there in the middle? Or should I write, is it okay? Or should I put ADC and then move the C over to the next step?
I think it's fine.
So you see, I'm really using the commutative property of real numbers here. Usually when you multiply by C, you would multiply in the same place. Like I would say, okay, I multiply both sides by C, and then this equals AC times D. But that shows that AC divides BC, right? Because AC is an integer multiple of BC. So I could just say, thus AC divides BC. I've already said D is an integer, so I don't need to say it again. Okay? Any questions? Yes?
You don't have to like point out that it is a multiple before you take the AC divided BC?
I mean, you mean, so maybe I should say then BC equals ACD? Is that what you're saying? I kind of jump from BC equals ADC equals ACD, but doesn't this show that BC is AC times an integer?
I don't know. I mean, does that suffice?
Yeah, I mean, I'm getting maybe a little looser with my rules. I mean, shouldn't I say then BC equals ACD? Is that what you want? Where D is an integer?
No, I'm saying like just by looking at that. But after we put that, we have to say thus it is a factor of. I mean, it is a multiple of.
You think I don't even need this line, this last line?
No, I'm saying should there be another step between that line, where you're like telling the reader that therefore it's a multiple of blah blah blah.
No, this is the definition of AC divides BC. What is the definition of this? Means that BC equals AC times an integer. This, you know, and I'm also using the fact that, you know, D is an integer. I could say for some. I mean, you know, when I first wrote these proofs, I literally wanted you to write the definition of you know, something divides something. That's the definition. AC divides BC means that BC equals AC times an integer. And I'm getting that from this statement right here. BC equals AC times D.
I think what she might be getting at is being like, say, then BC equals ACE for some integer E equal to D.
Well, I've already got an integer, an arbitrary integer D. So I don't need another. I don't have to replace D with another arbitrary integer E. Okay. Okay.
How can you get them at AC equals ACD?
Say again.
If your final is AC divided by BC,
Yeah.
and you have BC equals ADC, where did the D go?
It's the same D. I mean ACD. I moved the
just
C. I moved the C next to each other. You guys. I mean, is it better if I write like this, or? I mean,
Where does it go in the last paper?
Because
That's
BC
AC
equals
divided by BC.
BC equals ACD.
This is an integer. This integer divides this integer.
Okay, I got it now.
Means that this times another integer equals BC.
Okay.
So I think you guys are using the fact that, I mean, we're talking about two letters dividing two letters. It looks a little different than just this. Okay. So I proved the forward implication. I proved A divided B implies AC divided BC. Okay. Now, to tell the reader what's going on, you need to let them know that you're about to switch the direction here. So now I say something like this. Maybe start a new paragraph and say, conversely, suppose, so that indicates I'm proving the converse now. I just proved P implies Q, now I'm proving the converse, Q implies P. Conversely, suppose AC divides BC. When will I be done with this half? When I've showed that A divides B. Okay? So what does it mean that AC divides BC? Then BC equals AC times an arbitrary integer. It's called V. Right? For some integer D. Okay? Alright. Well, how do I get from this to a statement like B equals AB? Divide both sides by C. Am I allowed to divide both sides by C?
Don't have a rule for that.
Well, when do we have to worry about dividing by an integer? I mean, what's some rules we have to worry about? We have to worry if C was 0. You know, if C could be 0, if I just said C was an arbitrary integer, that doesn't rule out 0. But do I know that C does not equal 0? Yes, because we said C is an integer. I mean, it starts a natural number, right? Our very first thing is ABC are natural numbers. All right, so we can divide by C. Okay, these are little things, but you can't just arbitrarily divide by stuff. You got to make sure you're not dividing by 0. Okay. So since C is a natural number, we can divide both sides by C to obtain that's right here. Obtain P equals AD. That's the definition of A divided B. already said, I mean, I don't need to say that b is an integer. I've already got that. So I would just say, okay, therefore, a divides b. And if you want another sentence in there, you would say, then b equals ad for some integer d. Therefore, a divides b. Okay? Done. Questions? Yes.
When you're noting which direction you're going to, some people put the implication symbol like in the direction. Can you just do that?
Yes, and I'll do that in the next group. Yeah, so that's exactly what I would. That's the way I prefer to do it too. And this is another way to do it. I mean, this uses more words, so that's why I don't prefer that method. But it's fine. And, this is more like you're writing an essay. It's one complete essay. It's got two halves. You got two paragraphs. First, we show the forward implicatives. Conversely, we do prove this statement. But somehow you got to let the reader know which direction, which half you're working on. I could have started with this half. You don't have to start just because P implies P if and only if Q. You can start with this half. Okay. Any other questions? All right. Okay. Let x be an integer. Prove 0 divides x if and only if x equals 0. Rather feeling uncomfortable already? Saying that 0 divides some other integer? Yeah, remember, our definition of division, a divides b, has nothing to do with a fraction. Right? It's actually a multiplicative statement. All right. So this is what Jenny was saying. Sometimes when you do these proofs, instead of saying, first we'll show that 0 divides x implies x equals 0. Instead of saying all that, I would do this. I put it in parentheses a forward arrow. So that tells forward implication. That tells the reader I'm proving this implies that, right? Because this is like an if and only if statement. So first I'm going to do this implication, then I'm going to do this implication, and that'll give me the if and only if statement. Okay. So just having this little notation, it's clear that I'm assuming. So I'm trying to prove this implies that. Okay. So suppose x is an integer and 0 divides x. So what is the definition? Just use your definitions of division. A divides b, right?
X equals 0 times a. First one is a.
Then x equals 0 times a for some integer a. Isn't it pretty easy to conclude that x equals 0? Because 0 times any integer is 0. So I would just say, thus, x equals 0.
You don't need that.
So I mean, maybe I should say, I think it's pretty obvious. If x equals 0 times a, then x equals 0. But you could say, because 0 times a is 0, or something like that. Okay. And I need to tell the reader I'm going to do the reverse implication. So now I will assume x equals 0 and show that that implies that 0 divides x. Okay? So suppose x equals 0. Now what do I need to show that 0 divides x? I I need to show that x equals 0 times an integer. Well, take your pick. What integer? I mean, you can use any integer, but how about something? Typically, you use the smallest. I mean, the smallest example that would work. If x equals 0, doesn't x equal 0 times 1? So therefore, Therefore, 0 divides x. I mean, do I need to say that 1 is an integer? I mean,
Instead of putting 1, can you put a variable so it works for any integer?
I guess you could, but then you're making then it's almost like you have to prove that 0 times any integer is 0. So this is simpler, probably. I mean, I actually would be wrong. You'd say then x equals 0 times a for any integer a. I mean, you can say that. I think people would buy that, right?
We're just writing the symbol for integers. Or
No, that is 0 times a set is not defined. 0 times a set of integers, and you need an integer. So I mean, it doesn't matter which one you choose, because the definition is, x equals 0 times some integer. Well, here is some integer. This kind of leads to the next type of proof of this. Anytime you have a statement about there exists, then all you have to do is produce one example to show that's true. Okay. We're done. So this is kind of a nice way to kind of break it up. It's clearly two different halves of the proof. Okay. But this is typically how an if and only a statement is proved. Okay, you actually kind of break it up into two parts. So don't call them cases. I'm not cases. It's the forward implication and the reverse implication. So P implies Q and Q implies P. Okay, any questions? All right. So then 7.3 talks about these existence proofs. So that's the last thing I'm going to say in chapter 7. All right. 7.3, existence proof. So these statements say there exists something. Okay, those are the form of these theorems. So to prove an existence statement like there exists an x such that p of x is true. Okay, so this is what these statements look like. They'll say there exists something. Okay, to prove there exists x such that p of x is true, all you have to do is provide one example of an x that makes p of x true. So provide an example of an x that makes p of x true. Okay. So here's the proof. Prove there exists an even prime number. Proof. Well, we just have to show a specific number or example that shows this is a true statement. Well, there's only one number you can use to show this exists, right? Number 2. So you say something like, I don't know, consider the number 2. then clearly 2 is even and prime. Done. That's it. It's kind of a simplistic example, but it's just to illustrate the idea of these existence proofs. You just have to prove one example.
That would make a good final question.
All right. How about a better quiz test question? Prove there exist integers m and n such that 2m plus 7n equals 1. This would take a little bit of scratch work. I mean, you wouldn't want to sit here and try to work it out like while you're doing it. I mean, you might just start playing around with integers. Find integers that you can plug in for m and n to make this equation true. Anybody find one?
Solve for one of the integers and plug it in for the other one.
What is it?
4 and -1.
4 and -1? Somebody else said?
-6 and -2.
-6
I was
and...
multiplying, just kidding.
Okay.
Forget that.
There's a -3 and 1. Okay. So, you know, not one of those pairs is the right answer. I mean, all you need to produce is one example. Okay. So prove. Let. What was the first one? First example, what did you come up with? 4 and -1. Okay. So m equals 4 and n equals 1. So let m equals 4 and n equals -1. Then 2m plus 7n equals 2 times 4 plus 7 times -1 equals 8 minus 7 equals 1. Done. I mean, do I need to say that 4 and -1 are integers? I mean, you could always add more details. I mean, but we know 4 and -1 are integers. So you could restate the sentence if you want to be add more details. Therefore, there exist integers m and n such that 2m plus 7n equals 1. But I think anybody would be satisfied that you produce 2 integers to make this work. And this isn't the only correct proof, right? I mean, somebody came up with another example. With -3 and 1, is that what it was? Okay. So, some existence proofs, these are called existence proofs, right? There exists something. There exists integers. There exists a prime number or whatever. So some existence proofs, some existence theorems, these are existence theorems, state that there is exactly 1x in other words, a unique x. There's exactly 1x, or there's a unique x for which a statement p of x is true. Okay, so sometimes these are called uniqueness theorems. There's, that statement I have over here, it says there exists an even prime number. I mean, you could strengthen that theorem and say there exists a unique even prime number, but the proof would be different. All I've done is prove that there's at least one. I didn't show that there's the only one. Okay, so uniqueness theorem, these are called uniqueness theorems. these are called uniqueness theorems. Okay. Okay, uniqueness theorems. Okay. So there's really two things you need to do for a uniqueness theorem. You need to show that at least one x exists that makes p of x true. But then you need to show that there's exactly one. Okay? So oftentimes there's two parts. You would show that one x makes this true. Then you would show that it's unique. There's only one that makes this true. I'll give you an example. Well, let me write that up. So it's proved. Let me come over here. I need some more room. Need a bigger chalkboard. Or I don't know if that doesn't erase very well, so I don't use it. Okay. Here's a uniqueness theorem. Prove the equation 2x plus 3 equals 0 has a unique solution. Okay. So there's really two steps. Okay. So kind of note here. Step one, we need to show there is a solution. Second, we need to show the solution is unique. There can only be one solution. You know that no solution can be very unique. Nothing can be very unique. It's unique. It's unique. It can't be more unique than very. And I had an English teacher that didn't like the one you used. Very unique.
Do you know how to catch a unique rabbit? Unique up on it.
Unique up on. I never really thought that. I couldn't remember what. Unique New York. Say that 5 times fast. All right. All right. Here we go. Proof. So let's find a solution for this. Okay. Well, yeah. I mean, if you plug, you see if the solution is negative 3 halves. Okay. So since let me plug in negative 3 halves. So that's kind of like scratch work. You know, you solve an equation and you find the solution. Now we know the answer is negative 3 halves. Okay. So since 2 times negative 3 halves plus 3 equals, well, the 2's cancel here, so it equals negative 3 plus 3 equals 0. Negative 3 halves is a solution. Is that clear? So negative 3 halves is the solution. You can plug in the equation, you get a true statement. All right. Now let's show that it's a unique solution. So this is often how I'll prove like this goes. You suppose you have 2 solutions. Okay. You know basically like a proof of contradiction, right, or something. Kind of like a proof of contradiction. Assume there's more than one. Well, then you have to conclude that they have to be the same number. Okay. This is how it works. So suppose x1 and x2 are both solutions. Okay, I'll be done when if I can logically conclude that x1 equals x2. That means basically you didn't have 2 solutions; they're the same number. Okay, suppose x1 and x2 are both solutions. Okay, then they satisfy this equation. Okay, so then 2 times x1 plus 3 equals 0. But that also equals 2 times x2 plus 3. Okay? So I can plug x1 and x2 in this equation, and they both equal 0. So what I'm going to do, I'm going to subtract 3 from both sides of this equation. Okay? Then we're subtracting 3 gives 2x1 equals 2x2. That's really what I'm trying to just isolate the x1 and x2. Yeah. Then dividing both sides by 2 gives x1 equals x2. So you can't have two different solutions. If you have two solutions, then they're actually the same number. Okay, so we're done. Let me just summarize it. Therefore, 2x plus 3 equals 0 has a unique solution. I'm going to say negative 3x.
They would move the definition of 0, the addition of the integer with the opposite of that integer.
Definition of it is a0,
Like
or
a,
the number
or a plus minus a equals 0.
So you think of the definition of an additive inverse. For every integer a, there exists an additive inverse negative a, such that a plus negative a equals 0. Yeah. But that's not really what we're.
Would you have to put the 0 in there when she's going to equal each other? Where it says the 2x, x1 plus 3 equals 0.
Yeah, I mean, why can we set this equal to this? Because they both equal 0. That's all. That's all. You dealing with that. Yeah. So they're both solutions. So therefore, 2x1 plus 3 equals 0. But 2x2 plus 3 also equals 0. So these are equal to each other. Okay. So we show that a solution exists, and we basically show that if you have two solutions, they're really the same number. They have to be the same number. So there's only one solution.
So is that like the same as if we had something like the quantity of x minus 3 squared? Or we had two solutions?
X minus 3, the quantity squared.
Yeah.
Quantity squared equals 0.
Yeah, where x equals 3 would be our only
Yeah,
solution.
and that would work because when you take the square root of 0, 0 is the only number with one square root. Square root of 0 is 0. I mean, if this was like any positive number, now you have two solutions. You have the positive and negative square root. Okay. That